Machine learning models are increasingly used to inform decisions that impact individuals and communities, and it is crucial to consider the long-term impact of such decisions. In this work, we present a theoretical framework to model such long-term impact using the notion of policy regret in multi-armed bandits. We can use this framework to evaluate decision-making algorithms, but also to design new ones with the long-term impact in mind. Let me start by introducing an example. Assume there is a budget planner that has to distribute resources among several communities. In each time step, the budget planner can provide resources to one of the community, and ultimately they want to maximize the long-term well-being of all communities. The budget planner does not know at which rate the different communities can benefit from additional resources and how this rate might change in the future. But let's say the budget planner knows from their past experience that the benefit of providing additional resources to a community will increase initially because the community can use additional resources more effectively. However, the benefit will be concave and at some point start to decrease as additional resources are less effective compared to previous ones. The benefit of the community as a function of the resource provided therefore might look something like this. The budget planner's goal is to use this knowledge in order to maximize the long-term benefit of their decisions. We model the situation as a multi-armed bandit problem, where each community is represented by one arm, and pulling an arm corresponds to providing resources to this community. However, the rewards here do not come from a fixed distribution, but they change as a function of the number of times an arm has been pulled. We therefore define the single-peaked bandit problem, which is a non-stationary bandit in which the rewards first increase and are concave, and at some point start to decrease as a function of the number of times an arm has been pulled. So these are exactly the same conditions as in the example before. We formalize maximizing the long-term benefit by the decision maker having to minimize policy regret. Policy regret compares the sequence of actions the decision maker chooses to the best sequence of actions in hindsight. This is in contrast to the more commonly used notion of external regret, which at each point in time compares the decision maker's action to the best action given the history so far. Importantly, policy regret considers the best sequence of actions, while external regret only looks one action ahead. Because of this, policy regret better captures the impact of the decision maker's actions on future rewards, and it is a natural tool to describe the long-term impact of decisions. In general, it's not possible to achieve sublinear policy regret in adversarial bandits, and therefore we need additional knowledge about how rewards can change, as we have it in the single-peak bandit in the form of constraints on the functional shape of the rewards. So let me now give you a brief overview of a related work and how our work fits into it. So the impact of machine learning-based decisions is extensively studied in the fairness in machine learning literature. Most work, however, focuses on one-shot decision-making scenarios, such as classification. More recently, there has been some work that looked at longer-term consequences of decisions. However, most of this work is focused on strategic responses to machine learning-based decisions and does not directly model the long-term impact as we do it. One very related line of work that looks at a very similar setting considers fairness in online learning, which is also a sequential decision-making problem, and they also use bandit models similar to how we do it. However, the concrete notion of fairness that's used in this line of work is still more short-term than our approach of using policy regret over a long time horizon. From a technical perspective, we use the framework of multi-armed bandits, which has been very successful in a wide range of applications. For our purposes, it makes sense to distinguish between stationary multi-armed bandits, where the rewards come from a fixed distribution, and non-stationary bandits, where the rewards can change depending on the decision maker's actions. Our single-peak bandit is a non-stationary bandit problem. So our work uses this non-stationary bandit to address the long-term impact of ML-based decisions and can therefore be seen as connecting these three areas. So let me now introduce the algorithm we propose for the single-peaked bandit problem. We call it single-peaked optimism, or SPO. SPO implements the principle of optimism in the face of uncertainty. We operationalize this principle by always pulling the arm with the highest optimistic cumulative future reward. So this is the arm that has the highest potential to yield high rewards in the future. To compute this, we have to distinguish between arms that are where the rewards are still increasing and arms where the rewards are decreasing. We know that increasing rewards will never increase more than linearly because they are concave. We can therefore extrapolate the last two observations linearly and use this as an optimistic bound on the future rewards. The situation is easier for decreasing rewards, where we can simply use the last observation as an upper bound because we already know that the rewards will not start increasing again. In our paper, we show that SPO achieves sublinear policy regret when observations are noise-free. The rough proof sketch goes like this. First, we show that all arms have finite asymptotes. Then we show that if you knew all of the asymptotes, you could choose a strategy that always pulls the arm with the largest asymptote in order to achieve sublinear policy regret. Finally, we compare SPO to this strategy, and the key step is to show that SPO pulls all arms with suboptimal asymptotes less than linear in the time horizon t. This means that these arms also contribute only sublinearly to the total regret, and we get sublinear policy regret in total. While this result only holds for noise-free observations, we also provide a heuristic for extending SPO to noisy observations. The idea here is to find an upper bound on the future rewards by using confidence intervals around past observations. For example, we might have observed the purple points in this plot, and we know that the true reward function lies somewhere within the confidence intervals around. We now want to find the function that provides the largest future rewards, and that is explained by the past observations. In the paper, we formulate this problem as a linear program, which exactly gives this red function here as a solution. In case the linear program is infeasible, we know that there is no function that is still increasing, and that explains the past observations. In this case, the function must already be decreasing. For decreasing functions, it's again simple to find an upper bound because we can just take the upper confidence interval of the last observation because we know the function will not start increasing again. Together, this gives us a way to upper bound the future cumulative reward from noisy observations, which allows us to implement SPO. The performance of this implementation will of course depend on the tightness of the upper bounds, but we show that this works very well in practice. So let me now show you some empirical results. First, here's a set of synthetic reward functions. In this example, arm 2 is better than arm 1 asymptotically, but arm 1 is better initially. We compare SPO to a range of common bandit algorithms evaluated using policy regret. Concretely here, we plot the per step regret, which is simply the policy regret divided by the time horizon t. So one point in this plot will be one experiment with time horizon capital T, and we report the total policy regret of this experiment divided by t. As baselines, we first have some simple heuristics, such as a greedy algorithm that always pulls the arm that was best the last time it was pulled. We have a one-step optimistic algorithm that also extrapolates the past observations optimistically, but it only looks one step ahead instead of the whole time horizon. EXP3 is a common algorithm for adversarial bandits. However, it is designed to minimize external regret instead of policy regret. Discounted UCB and sliding window UCB are variants of the commonly used UCB algorithm that are designed to work for non-stationary bandits as well. However, they mainly tend to work well when the changes in the reward function are limited. REXP3 is a modification of EXP3 to minimize policy regret in non-stationary bandits. Finally, SPO is shown in red. Here are the results. You can see that the simple heuristics completely fail to explore both arms, and they only pull arm 1, which is better initially. REXP3 also never stops exploring the suboptimal arm because it regularly reinitializes its estimates of the reward distribution. The other methods are all eventually able to discover the optimal arm, but they take much longer than SPO. Overall, SPO performs much better than all alternatives, except for very short time horizons. Next, here's an experiment that is based on real data. Here, we simulate a situation similar to the initial example with the budget planner, using the FICO credit scoring dataset. We use this dataset to simulate a population of individuals, which we then divide into different racial groups. We then compute reward functions that simulate the benefit of giving loans to each of the groups. But as you can see, these reward functions do no longer exactly satisfy the assumptions of a single peak bandit. So for example, they can increase again a bit after they started to decrease. But by using a Gaussian noise model with large enough variance, we can use the same algorithm as before. Again, we compare SPO to the same baselines as before. And again, we find that it achieves much lower policy regret than other methods for long time horizons. For short time horizons here, the simple greedy heuristics are preferable because they immediately start exploiting to get high rewards. But this is also what we would expect because SPO is designed to achieve better performance when evaluated over long time horizons. So it takes more time to explore kind of the other arms initially. In this example, all methods eventually achieve sublinear policy regret, but this is only because the rewards of all arms drop to zero eventually. In the last experiment, we consider a simulated recommender system. Here, each arm corresponds to a different item that can be recommended to a user. There is some inherent benefit that the user gets from each item. However, novel items might be more interesting to the user at first, but then the user might quickly become bored of them. These assumptions create a reward structure that we can describe by a noisy single peak bandit. The reward increases initially because an item is novel, and then it decays. Then the reward decays towards its asymptotic value. The goal of the recommender here is to recommend items that give the best inherent benefit to the user and not get stuck recommend something that was only good initially. Again, we compare SPO to the same baselines as before. The results show that SPO again significantly outperforms all other methods. And here, none of the other methods comes close to achieving zero regret within this time horizon that we tried. This simple simulation shows a separate domain in which single peak bandits might be useful. Okay, to summarize. I said that it's important to model the long-term impact of ML-based decisions, and that such modeling requires using domain knowledge about the effects of different decisions. Then we introduced policy regret as a way to measure the long-term impact of decisions. And we looked at a concrete setup that we called the single peak bandit problem. And here the domain knowledge came in the form of knowledge about the functional shapes of rewards. We introduced SPO and showed that it achieves sublinear policy regret in this setting. And finally, we introduced a heuristic to handle noisy observations and demonstrated empirically that this algorithm works well in a range of simulated experiments. If you want to learn more about the details, feel free to come visit our poster or read the full paper here. Thanks a lot.